Hello everyone, I'm Crystal from Rice University. Today, my group and I would like to present MXDAG, a hybrid abstraction for emerging applications. This work is led by my colleague Rita and also worked with Shuan Zhuang, advised by Professor Ang Chen and Professor Eugene. First, let me introduce some background. Nowadays, there's an increasing number of trending cloud applications and frameworks, such as Bug, distributed training, Amazon Lambda, and so on. These applications usually require two different kinds of resources, which are both critical. On the one hand, the computational tasks running on the host rely on the compute resources like CPUs, GPUs, and accelerators. On the other hand, all the applications, all the hosts, would share the network resources like bandwidth. Then there come several questions. How to schedule the resources to improve the application performance and resource utilization? How to share the resources among multiple applications? The existing solutions encounter three main shortcomings. First, previous DAGs lacks explicit network code scheduling. They mainly focus on the computational tasks while ignoring the communication tasks and treat the network as a black box. Let me give an example here. There's a job with three flows. Flow 1 and Flow 3 are both sent from the host A. Without code scheduling, flows 1 and 3 start at the same time and share the same link bandwidth equally at host A. However, a better strategy with code scheduling would better prioritize the flow 1 over flow 3, so that flows 1 and 3 can enjoy the full bandwidth independently. Therefore, task B can start earlier, and this can reduce the overall completion time. Next, John will introduce the other two shortcomings of existing work.
Another popular abstraction is called Coflow, which can schedule a group of flows to minimize the overall communication time. Coflow focuses on the network resources, but you cannot get aware of the critical path if it is a compute resource. In this example, we have three tasks, and task A has much longer execution time than task B. If we group flow 1 and flow 2 as a coflow, then you can lead to suboptimal performance. However, if we can begin the communication of flow 2 right after the execution of task B, we can improve the performance. We also observe that coflow abstraction can harm the performance for asymmetric DAG in terms of both topological asymmetry and computational asymmetry. Pipelining is a promising technique to reduce the computation time by overlapping the communication with the computation. But neither DAG nor Coflow can analyze the possible probability of jobs. In this example, we also have three tasks. And this figure shows the optimal scheduling without any pipeline. If we overlap communication of flow 1 with task A, we can improve the performance. However, if we also overlap the communication of flow 3 with task A, and then flow 3 has to compete for the network resources with flow 1 and delay the execution of task B, resulting in degraded performance. Based on these observations, Suvan will introduce the definition and benefits of MXDAG abstraction.
So, based on the previous example, we can infer that we need a better abstraction to make the co-scheduling possible. For that, we need to explicitly consider both the compute and the network task to find out the end-to-end critical path. Second, we need to allocate the resources to optimize the performance of such critical path, because critical path performance actually represents the end-to-end application performance. Third, we need to schedule the pipelining carefully while taking the resource sharing into the consideration. So the important benefits would be we would have a finer grained view of the application. We would have better critical path analysis, and these two will eventually improve the application performance and the resource utilization. So in the next slide, we show our proposed hybrid compute network abstraction called MXDAG. So MXDAG consider compute or the network task both as explicit node, which we called mixed task, and the edges represent the dependencies between these mixed tasks or nodes. For example, as we see a left-hand figure, a traditional DAG where A, B, C, D are the compute tasks and F1, F2, F3, F4 are the 4 network tasks. And now we can see the mixed DAG counterpart where all these tasks have been represented as specific nodes and there are edges between them. Now each node has two important attributes here. First, it's called size, which is the ideal completion time of an individual mixed task, while optimal amount of resource was allocated for that. And second is called unit, which is used for the pipelineability analysis, which is the smallest unit size under pipelining. For example, if we focus on F2, the task F2, it has size 4 and unit 1. It means 1/4 of the task F2 need to be finished, and after that we can actually start the next task C and put it into pipelining. Similarly, task C has size 4 and unit 1, which means again 1/4 of task C should be finished at minimum, and from that point we can actually start the next task F4 and put it into the pipeline. So from the next slide, we are going to show the major use cases of this abstraction MXDAG, which is going to be presented by Weta Wang.
Thank you, Showan, for introducing the definition for MXDAG. I will briefly introduce some principles when using MXDAG for scheduling. To schedule a single MXDAG, the key principle is to prioritize the end-to-end critical path because it dominates the job completion time. Here we show an example job in the following figure. If we start both flow 1 and 3 immediately after task A, the timeline is shown in the bottom figure. We can see that the flow 1 and 3 share the NIC bandwidth of host A. However, since flow 1 is on the critical path, we should follow the principle and prioritize flow 1 over flow 3. Then the flow 1 can use all the bandwidth and finishes earlier. Thus, all the following tasks on the critical path will also start earlier and reduce the completion time. If we have multiple applications or jobs, we have to schedule multiple MXDAG at the same time and share the resources between them. In this case, the key principle is to let every application to be altruistic, which means the application will try to benefit others without hurting its own performance. One of the methods is to delay the execution of the non-critical path until necessary. In the following example, we have two jobs and some of their tasks share the same resources on the host B. Normally, the two tasks on the host B start at the same time and share the resources equally. However, since the task B and flow 2 are not on the critical path, we can delay those tasks without hurting job 1's performance. By letting the tasks from job 2 finish earlier, job 2 could largely reduce its completion time, while job 1 remains the same performance as before. There are many other usages for MXDAG. Here we introduce one of them, which is a runtime closed-loop control. At the beginning of the execution, we can find an initial critical path based on the MXDAG. While at runtime, we could monitor the progress of each task and find out the stragglers in the application. In this case, the bottom path is much more slower than other passes and becomes a straggler. Thus, we could reschedule the resources since the bottom path has become the runtime critical path for this application. In summary, we propose the MXDAG, the first comprehensive abstraction for emerging applications. MXDAG treat compute and network tasks equally and introduce runtime reconfigurable Pipelineability in the application. We also provide two principles for co-schedule the compute and network resources. We prioritize the critical path within a single MXDAG and require the application to be altruistic when we have multiple MXDAG. And we also briefly introduce some other usages, including monitoring the path-wise progress at runtime and mitigating the stragglers with a global view. I think this concludes our talk, and we are happy to take any questions. Thank you.